Good morning, good afternoon, and good evening to everyone joining us from around the world. Welcome to the VTS Young Professional webinar. We are delighted to have you with us today for an engaging and insightful webinar session. I'm Shadlia Ben Naila, Secretary of the VTS Young Professional Committee and the coordinator of the Young Professional Webinars series. Today, we are pleased to host Dr. Ji Gao, Associate Professor at Carleton University. Dr. Gao is an Associate Professor at the School of Information Technology at Carleton University. His research focuses on machine learning for communication and networks, digital twins, and other emerging technologies for 6G. Dr. Gao is the recipient of the 2025 IEEE VTS Open Journal of Vehicular Technology Best Paper Award and the 2024 IEEE Best Land Transportation Paper Award as well. He has served as publicity co-chair for the IEEE VTS 2025 Fall and IEEE Metacom 2023, publication co-chair for IEEE IoT DI 2022, and co-chair actually for multiple tracks and other symposia, workshops of IEEE international conferences. We are delighted to explore his perspectives on edge intelligence empowered integrating sensing and communication to case studies with digital twins. Without further delay, please join me in warmly welcoming Dr. Gao Che. And Dr. Gao, the floor is all yours.
Thank you so much, Professor Shadlia, for your kind instruction and for organizing this webinar. And I'd like to thank everyone who's here for your attention and participation. So allow me to share my slides again.
Yes, thank you.
Okay, just checking the slides are visible.
Yeah,
okay,
indeed.
Great. Yeah. So the topic of my presentation today is Edge Intelligence Empowered Integrated Sensing and Communication to Case Studies with Digital Twins. I'd like to thank IEEE VTS Young Professional Webinar for hosting this presentation. This is collaborative research conducted with Professor Shisheng Hu, Professor Cunghao Zhou, Professor Mushu Li, who graduated from University of Waterloo, and Professor Xuanming Shen and Professor Weihua Zhuang at University of Waterloo. So there are 4 parts of this talk. First, I will give a brief introduction to ISAC, EI, digital twin. Then I will introduce the 2 case studies. And at last, I will make the conclusion. So introduction. The concept of ISAC is self-explanatory, basically one system, 2 functions. On the communication side, the purpose to transmit data and the targets are usually active, meaning that they have transceivers and they are connected to the network. On the sensing side, the goal is to detect and estimate the characteristics of targets such as position, speed, and so on. And the targets are likely passive, meaning that they may not have transceivers, they may not be connected to a network, such as humans moving around or even animals moving around. The benefit of ISAC is that it integrates data collection and data transmission. The sensing part provides context for communication, and the communication side can support timely sensing data delivery. And with edge intelligence, we can further integrate data processing. There are many emerging ISAC applications. The first one is human-robot collaboration. This is considered as one of the main applications in Industry 5.0. Other applications include intelligent transportation and autonomous driving, detection and tracking of UAVs, say by cellular base stations, and extended reality and metaverse. So the communication side is for streaming immersive content, and the sensing side is for tracking player motion and so on. There are many standardization organizations working on ISAC. For example, ITU, 3GPP, IEEE, and IETF, they have all developed related technical documents or standards on ISAC. We can categorize ISAC into different types. By integration level, we have the 5 types here. And the first one just says, okay, we have 2 sets of hardware, one for sensing, one for communication. They're simply placed at the same site. And the second one is still 2 sets of hardware for sensing and communication, but then they are sharing the same spectrum. The third case is we have now 1 set of hardware for both sensing and communication. The fourth one is reusing waveform. For example, in OFDM, some subcarriers can be used for sensing, some can be used for communication, and the last one is reuse of signals. This will be, for example, one subcarrier used for both sensing and communication. According to Ericsson, the first 3 cases are more likely in near term. And we can also categorize ISAC based on the number and location of transceivers for sensing. In the first case, shown here, we have monostatic sensing. So one transceiver both emits the sensing signal and picks up the reflected sensing signal. And the second case is bistatic sensing. So we have 2 different nodes. One emits the sensing signal, the other picks up the reflected signal. And the third case is multistatic sensing. Multiple nodes, one or more of them emits the sensing signal, and one or more of them picks up the reflected signal. So how's edge intelligence related to ISAC? So basically, edge intelligence can do 2 things related to ISAC. First, processing ISAC data. So we can deploy AI model on edge server for sensing data processing. For example, for detection, for detecting motion based on the collected sensing data samples. We can also use edge intelligence for managing ISAC. This can include managing ISAC resources, coordinating ISAC devices, say in the case of collaborative sensing, and evaluating ISAC solutions, for example, by emulation. And there are some challenges to edge intelligence empowered ISAC. And the key challenge, which is the focus of this talk, is data drifts. And data drifts means change in the statistical properties of data over time. And here we have 2 examples. The first example is data drift in the sensing target distribution. So initially, the sensing target distribution can look like this, but over time, the distribution, spatial distribution can change to either this case or the other case shown here. And the second example is the drift in reflected sensing signal. And this may be caused by a reduction in the sensing duration. So say initially we have longer sensing duration, and then the reflected sensing signal can look like this. However, later, due to increased communication traffic load, we need to reduce the sensing duration. So the reflected sensing signal may look different. The challenges caused by data drifts to EI-empowered ISAC includes 2 aspects. First, challenge to processing ISAC data. When the collected sensing data samples look very different, the accuracy of AI models deployed on edge can degrade. Second, challenge to managing ISAC. So data drifts make the environment even more dynamic, and this can lead to difficulties in resource reservation. One thing that I'd like to emphasize here is data drifts doesn't just mean time varying. So the environment would be time varying in any case. Instead, data drifts emphasize the change of the underlying probability distribution or stochastic process. So how can digital twin be used to address this challenge? Well, in multiple ways, but in order to expand that, I'll first briefly introduce the concept of digital twin. The general concept of digital twin is familiar to many people now. Basically, it means a digital representation of a physical object and usually it features real-time synchronization between the object and its digital replica. Our focus, however, is not an exact and precise digital representation of a physical object. Instead, we define digital twin to be a configurable and adaptive data profile and associated data processing functions. And this definition allows us to use digital twin as a flexible and agile tool for modeling, decision-making, and decision evaluation. And here, flexible means we can define digital twin based on specific network environments, specific network use cases, or specific requirements. And agile means even for a given environment, application, and set of requirements, the digital twin can evolve over time to adapt to the dynamics of the network. So there are two types of digital twins in our early work, early tutorial about digital twin and AI for 6G. So the first type is user and device digital twin. And this type of digital twin characterizes per user or per device service demand, quality of experience, channel information, and so on. And the purpose is to support user or device level customization and user or device centric service provision. The second type is network digital twin, and this means the virtualization of either physical or virtual networks. In the context of 5G, a virtual network can be, say, a slice. And network digital twin focuses on service-specific data, aggregated service demand, slice resource utilization, and so on. And network digital twin can support service diversification and service performance optimization. So how can digital twin help address the data drift challenge? Well, in two ways. First, digital twin can help us characterize data drifts. We can use digital twin to help model spatial distribution of sensing targets. We can use digital twin to model the accuracy of sensing data processing, and from those models, we can detect data drifts. Second, adapt to data drifts. So digital twin allows us to bridge theoretical and data-driven decision-making, and also help us emulate resource reservation solutions to identify the best performing solution. So far, everything is discussed on a high level, so the idea may not be very clear. In the case studies, I'll try to make things, the idea more clear. Okay. So the first case study is spatial modeling and drift detection in AI-empowered ISAC. And the scenario is shown here. So we have a network with multiple cells, and in each cell, there's one access point that is ISAC capable. And we have multiple mobile ISAC devices in each cell. And in this figure, a mobile ISAC device is shown as a mobile robot. And for each mobile ISAC device, it is only interested in targets in its region of interest, shown as this shaded circular area here. And it aims to track the targets, sensing targets, in this figure, humans moving around, in this region of interest. And the AP will also provide help. So from for the rest of this case study, I will focus on one AP and one ISAC device, unless otherwise mentioned. In order to understand how this ISAC system works, I'll first briefly introduce a timeline design, which includes 3 levels: time window, frame, and slot. So a time window, as shown here, is for proactive resource reservation. Specifically, by the end of the current time window, we should make a decision on the resource reservation for the next time window. And the frame is for target assignment or reassignment to the access point and ISAC devices. So the assignment of sensing targets can be different across different sensing frames. And each frame consists of multiple time slots, And a slot is used for either communication or sensing by the mobile ISAC device. And the probability of communication is rho c, probability of sensing is 1 minus rho c. One may wonder, why do we need to introduce this probability? That is because we aim to do proactive resource reservation, and it's impossible to tell exactly which slots will be used in future for sensing or communication. And knowing how the timeline works, next we'll expand the sensing mode. So basically there are two different sensing modes, targeted searching and target tracking. Target searching is conducted by the access point or AP only. So this means the AP will search for targets newly arriving at the region of interest ROI of ISAC device in each frame. It will also monitor targets leaving the ROI of each ISAC device. And by doing those, the AP will maintain a list of targets currently in the ROI of ISAC devices. The AP will not be able to know the accurate, say, position or speed of the ISAC device, but it will maintain a list of targets present in the ROI. And the second sensing mode is target tracking. So target tracking can be conducted at both AP and ISAC devices. However, each target is assigned to either AP or ISAC device for tracking, not both. And tracking happens continually across multiple slots. And the continuous tracking in a frame creates one sensing sample. So each frame, one sensing sample is created. And the sensing sample is processed locally, meaning that if a sensing target is tracked by the AP processes the sensing sample. If the sensing target is tracked by the ISAC device, then the ISAC device processes the sample. Since both AP and ISAC device track targets, so how do we assign targets between them? To keep things simple, we introduce this on-device sensing region, which is this inner circle in this figure. With a little abuse of the technical accuracy, what we do is if a sensing target is within the inner circle, the on-device sensing region, then this target is assigned to the ISAC device. Otherwise, the target is assigned to the AP. And the functioning of the ISAC system requires resources, obviously, and there are two types of resources considered here, spectrum resource and computing resources. And there are 5 different classes of the spectrum and computing resources. I will not read through them, but some of those are shared. The sensing and communication spectrum, they use orthogonal, the sensing and communication spectrum is orthogonal. So we have one sensing slice and one communication slice, and the sensing spectrum usage follows the following rules. First, the spectrum for searching and tracking is orthogonal. Second, the spectrum for tracking each target at each ISAC device is also orthogonal. However, the total available spectrum for target tracking is the same at all ISAC devices. This means there is no self-interference at each ISAC devices for tracking different targets, but there can be mutual interference between different ISAC devices when they conduct target tracking. For the ISAC system to perform well, we need to have some requirements. And here we have the 3 sets of requirements. The first is communication requirement. So the mobile ISAC devices may need to upload data to the AP, say the environment related data, and it will need sufficient time for uploading the data. And this translates to a lower bound on the slot communication probability, rho c. On the sensing side, we need to guarantee sensing sample quantity and sensing sample quality. For guarantee enough sensing samples, we need to have a lower bound on the slot sensing probability, 1 minus rho c, and we also need to have a lower bound on the sensing signal to interference ratio. This is because, again, different sensing devices, they share the same spectrum in target tracking. And the last requirement is to limit the sensing data processing time. Since sensing data samples are processed locally, we don't want to allocate or assign too many sensing targets to either AP or some ISAC device so that they keep accumulating more sensing samples than they can process in time. Now, with all that introduced, we're ready to introduce our research objective. So the objective is to proactively reserve resources to satisfy sensing and communication service requirements, and also at the same time minimize the resource usage. In other words, we want to use for a fixed set of to from resource reservation to sensing target assignment. And without going into technical details, I'll explain that the sensing target assignment, the initial two results we can derive are the following two: the expected number of targets that ISAC devices can track, given the resources and given the service requirements, and the expected number of targets that AP can track. And the problem is formally formulated as shown here. So again, the objective is to minimize all shared resources usage, and the constraints are satisfying the sensing and communication service requirements explained 2 slides ago. And there are 3 sets of optimization variables. First, spectrum and computing resource reservation. Second, radius of the on-device sensing region, so the size of the smaller inner circle. And the slot communication and sensing probability, so rho C versus 1 minus rho C. And we can show that the sensing target assignment depends on the spatial distribution of ISAC devices and targets. This is rather intuitive. And the modeling of the spatial distribution of ISAC devices and targets is referred to as spatial modeling for brevity. The challenge to spatial modeling is twofold. First, data drifts can happen to stochastic spatial distributions. Second, we need to strike a balance between the modeling granularity, robustness to data drifts, and tractability. And our approach is digital twin-based adaptive spatial modeling. And our overall digital twin design is shown on this slide. I will not mention the details, but only the high-level idea. And the first thing to explain is that in this case study, the digital twin is a slice digital twin. We have one for the communication slice and one for the sensing slice. And the digital twin data is locations of the ISAC devices and targets in the preceding windows. And the digital twin functions include the following 3: detecting data drift, updating spatial models, and emulating resource reservation derived given the spatial models. And I will briefly explain each of them. So spatial models, we introduced 2 different spatial models. The first one is called joint spatial model, and second is called independent spatial model. The difference is whether it considers the correlation between target and device locations. And for joint spatial model, we use the Thomas cluster process, and for independent spatial modeling, we use independent Poisson point process for the ISAC devices and the targets. So after determining the specific processes, what we need to do next is to determine the model parameters. So we collect ground truth locations in each window by the end of the window, and we fit the model parameters using maximum likelihood estimation based on the collected ground truth location, and using the fitted parameters from the past, we predict parameters for the next window using a long short-term memory network. And how do we detect data drifts using such a model? Well, basically, we calculate the parameter errors, which means the gap between the fitted parameters and the adopted parameters at the end of each window. And if this error increases above a certain threshold over multiple windows, we will conclude, okay, a drift has occurred. If no drift is detected, we keep using the joint spatial modeling because without data drift, has higher granularity and it's more accurate. If a drift is detected, then we do the following two things. First, we update the LSTM model. So we need to retrain the LSTM using the fitted parameters after the last drift. Second, we do a model ensemble. So we output both the updated independent model and the updated joint model, and we emulate the performance of resource reservation under these two models. And this brings us to the resource reservation emulation function of the delivery. The goal of the emulation is to compare resource reservation solutions derived under the two spatial models. So we're not directly comparing the spatial models, but comparing the resulting resource reservation performance. And we select the better performing one. And the emulation steps, in a very simplified way, include the following two. First, instance construction. So we create multiple instances using historical location data, each with a unique instantaneous spatial distribution of ISAC devices and targets. And then we evaluate the solutions. So we implement the candidate resource reservation solutions in each instance and compare their performance across all the different instances. So we mentioned how to do the spatial modeling, how to do the emulation, but we haven't mentioned how to actually reserve the resources. Now this page briefly describes how to do that. So recall that given the spatial modeling, we can derive the two expected values, expected number of targets in the region of interest of ISAC devices, and the expected number of ISAC devices in the coverage of the AP. These two values characterizes the sensing demand and the sensing capacity. And with these two values, next we can derive the optimal radius of the on-device sensing region. And with those analysis, we can next propose the conditions, necessary conditions for resource reservation solution to be optimal. And the conditions are shown on the right-hand side. I'll just briefly mention that with such conditions, the original problem reduces to optimizing a single variable, rho C, the slot communication probability, and this significantly reduces the complexity of the problem. Next, I will introduce some numerical results. The specific setting in experiment setting involves a lot of details, so I will skip most of the details and encourage you to check the paper. I'll just mention something on the high level. So the actual spatial distribution used in the experiments are different from both the independent and the joint in the experiments, depending on the specific example. And the benchmarks we compare our distribution-based solution with include the following four. So independent modeling in the ideal case, joint modeling in the ideal case. This means we assume ground truth locations are known for the next window, which is not realistic. And joint modeling and independent modeling with no drift detection or model update. This means we initially fit the parameters, but after the initial parameters, we do not update them at all. So this first experiment shown here involves 400 resource reservation windows, and a drift happens at window 201. And the three figures shows the service satisfaction ratio. So the ratio that the performance requirements are all met. the overall resource consumption, and the modeling error. So what the figure shows is in the first case, we see that in the two ideal cases, unrealistic cases, their service satisfaction ratio is high. And the proposed digital twin-based approach, the grain curve, has a relatively high satisfaction ratio. And the independent modeling, the blue curve also has a good service satisfaction ratio. In the second figure, what we see that independent modeling, in the ideal case or not, consumes a large amount of resources. In comparison, the proposed solution, the grain curve, achieves lower resource consumption. In the third figure here, we show the modeling error and the impact of the data drift on the modeling error. So the blue curve corresponds to independent modeling. So after the data drift happens, it's not impacting much. The red curve here corresponds to joint modeling. And in the case when we don't do model update, after the data drift, the error suddenly increases to a very high level and doesn't fall back. And with model update, the error increases first, but after the update, the error will gradually fall back to a low level. The second experiment is about the impact of drift frequency. So we gradually increase the number of drifts within a certain amount of windows and see what's the impact on service satisfaction ratio and resource consumption. So basically, we can see that, well, compared to the ideal case, of course, the proposed solution is not as good, but the ideal case, again, is unrealistic. Compared to the joint modeling with model update, this means we do not do the ensemble. We do not switch between the better one of the joint modeling and the independent modeling. Then the satisfaction ratio would be low and the resource consumption would be high. So in comparison, our proposed approach has higher satisfaction ratio and lower resource consumption. The second case study is adaptive sensing data processing in edge intelligence empowered ISAC. And the scenario is given here, which is simple. We have one ISAC device shown here, and this device collects sensing data. And for each sensing data sample, it's processed either locally on the ISAC device or offloaded to an edge server for processing. The ISAC device has a lightweight DNN with lower accuracy for processing sensing data locally, and the edge server has a large DNN model or larger DNN model with higher accuracy for processing the data sample. In addition, the edge server also has a library of lightweight DNNs in case the on-device lightweight DNN needs to be updated and replaced. So data drift may happen, as mentioned before, and here a data drift can be change of sensing duration. And when a data drift happens, the accuracy of the lightweight DNN will degrade significantly, and this is because the lightweight DNN is trained with limited data. The large DNN, however, would not be impacted nearly as much. This is because the large DNN is trained with extensive data. So after a data drift happens, the edge server would do one of the two things. If the DNN library contains a suitable lightweight DNN after the data drift to replace the on-device lightweight DNN model, the edge server will select that suitable lightweight DNN, send it to the ISAC devices to update the on-device lightweight DNN model. If the DNN library does not have such a suitable model, then the edge server will need to retrain a lightweight DNN to update the on-device lightweight DNN. So similarly, we'll introduce a timeline to explain how things function. So we have time windows and frames, and each frame contains two parts. At the beginning, a sensing duration, and then a communication duration. And in each frame, one sensing data sample is collected, and one sample processing task is generated. And the task, as mentioned before, would either be processed locally or offloaded to the edge server. And here we introduce an offloading probability, which means a probability of offloading the task to the edge server for processing. In each window, we have n frames, and we assume data drift occurs at most once. And we also make our offloading probability the same across all the frames in the same window. Say for the tth window, the offloading probability would be rho t. Since the edge server may need to train or retrain a new lightweight DNN if data drift happens and there's no suitable lightweight DNN in the library. So one may wonder, what's the data used for retraining? Basically, the data comes from offloaded sensing samples. And one thing to mention here is we do not use all offloaded sensing samples for retraining because this can be a very large amount of data and a high processing load. Instead, we assume only selected sensing samples would be used for training. So this leads us to a training probability, which is the probability of an offloaded sensing sample being selected for retraining a new lightweight DNN. In each window, we have fixed training probability for all frames in the window. So for the tth window, the training probability is gamma t. And with the sensing probability and the offloading with the offloading probability and the training probability, we now face an accuracy and computation load trade-off. So the offloading probability rho t affects the average accuracy of sensing sample processing. This is because local processing has lower accuracy, while if sensing sample is offloaded to the edge server for on-edge server processing, the accuracy is higher. However, if we offload a lot of samples to the edge server for processing, the cost for increased accuracy would be increased computation load on the edge server. The training probability affects the computation load for retraining. So in addition to task processing, if a lot of uploaded samples are used for training new lightweight DNN, then we have an additional training load. Jointly, the offloading probability and and training probability also affect the accuracy of retrained lightweight DNN. This is because if the offloading probability and training probability are both high, then more sensing samples are used for training. And with more samples used for training, the accuracy of the retrained lightweight DNN will increase. However, the exact relationship is unknown. So with that, we are ready to formulate the problem. The objective is to minimize the long-term average edge computation cost. So we want to support the ISAC system with minimum edge resource consumption. And the optimization variables are the offloading probability and the training probability. And the constraint here is minimum average accuracy. So we want the average accuracy for sensing sample processing to raise above a certain threshold. And since this average accuracy depends on the offloading probability, so equivalently, we have a minimum offloading probability requirement. And the optimization problem is formulated on the right-hand side. And the challenge to solving this problem is the occurrence of data drifts, which is not known precisely in advance. Second, the lack of an exact model of retrained DNN's accuracy versus the number of samples used for retraining. So to solve this problem, we resort to digital twin again. In this case study, the digital twin is a device digital twin, which is a representation of the ISAC device. And the digital twin data includes indexes of the time windows when recent data drifts happen, and the number of training samples and the resulting accuracy of the retrained data. And different functions include the following two: estimating the expected number of time windows between two adjacent drifts, and modeling the accuracy of retrained DNN. So we have some base model, but we will need to determine the model parameters. and the data drift would have an impact on the accuracy model. To describe the solution approach on a high level, so the first thing we need to do is to find the minimum task uploading probability that satisfy the average accuracy requirement. And that probability is shown as follows. And with that, the next thing we do is to reformulate the computation cost at the edge server. And we have three parts of the computation cost. The first is training cost. And the second is processing cost for the current window. And the next is processing cost for subsequent windows until the next data drift. And using this decomposition of the processing cost, we can transform the original long-term optimization problem into consecutive one-shot optimization problems. And if no drift is detected, we keep using the current solution. If data drift is detected, then we solve the following one-shot problem. This one-shot problem has a nice property that it is biconvex if the parameter bt, which is shown here, is in between 0 and 1, and it is biconcave if bt is larger than 1. So we can relatively easy, we can find the solutions easily using either alternate convex search or just compare two boundary cases. And when bt is in between 0 and 1, the closed form solution for each iteration is shown here. I will not go through the details, but just mention one thing. So here we have the training probability, and we have this capital T bar. This represents the expected number of windows in between two data drifts. So what this result says is if this T bar, the expected number of windows in between two data drifts, is large, then the training probability will also increase. This is because if there's a longer duration in between two data drifts, then the retrained DNN model can be used for longer. So there's stronger motivation to increase the accuracy of the retrained model by using more samples for training. I'll briefly mention some numerical results. Again, for details, please check the paper. The basic setup of the DNNs is shown here. I'm not going to read it. The benchmarks include the following three. First, heuristic or without DT. So in this benchmark, we assume, okay, we just use the minimum offloading probability that can satisfy the average accuracy requirement. And we use all retrained, all offloaded samples for retraining. Second is without distring update. So we establish an initial accuracy model, but after that, we no longer update this model. The last one is lower bound or the ideal case. So we assume perfect knowledge of future data drifts and accuracy of retrained model. And the first example compares the computation cost in the proposed and the benchmark schemes. From the figure, we can see that the proposed scheme, which is the shown in red, performs better in terms of computation cost compared to all realistic schemes. It's not as good as the unrealistic scheme, but then in the unrealistic scheme assumes future knowledge. The second example shows the impact of the data drift probability. So here we consider 10,000 time windows. We use an extreme case just to illustrate this point. In the first 5,000 windows, the drift probability is high, which is 0.3. In the second 5,000 windows, the drift probability is much lower, it's 0.075 in each window. And we see what's the training probability after solving the problem. And from the figure, we can see that when the drift probability is high, the training probability is relatively low. And when the drift probability is low, the training probability is high. This matches our analytical result, right? So when the drift probability is low, then the duration in between two data drifts is longer, and there's stronger motivation to use more samples to train the lightweight DNA in order to increase its accuracy. So in conclusion, we talked about edge intelligence empowered ISAC, how edge intelligence can be used for processing ISAC data and for managing ISAC devices, managing ISAC resources. And we mentioned our definition of digital twin, so basically data profile and data processing functions, and how digital twin can integrate data-driven modeling and decision with analytical models. And we discussed potential role of digital twin in edge intelligence empowered ISAC, detecting data drifts, adapting to data drifts, and we illustrated the benefits, so higher accuracy in data processing and lower resource consumption in ISAC resource reservation. And here are some references used for this presentation. And thank you very much for your attention.
Thank you very much, Dr. G, for the very insightful presentation. And I open the floor now for any questions from our attendee. You may reach out via chat if you would like to ask any questions to our presenter today.
Should I stop sharing? I cannot see the chat when this is shared.
I think it's still fine. So in case maybe
Okay.
you may get some question on the content of your slides,
Sure.
I think you can just leave there. At the moment, I don't see any questions from our audience. So if you don't mind, I will be asking a few questions.
Sure.
Take advantage of having you today with us in our webinar.
Sure, please go ahead.
I will start with a very general question. Like, what makes ISAC different actually from traditional separate communication and sensing systems? And I guess this is how you started your presentation today. So could you kindly expand further on that?
Right. So, yeah, so your question, if I may rephrase it, is basically what makes ISAC unique and beneficial compared to having two separate systems,
yes,
one for communication and one for sensing, right?
Yes.
Yeah, we can look at this from different perspectives. First, from a practical perspective, right? So there's strong motivation if you can use one set of system to achieve two purposes. That saves the capital cost, that reduces the operation cost, right? And so that's the main motivation when why the research community is very interested in ISAC, the practical side of things. Now, technically, if we say, okay, we have two different set of systems, one for sensing, one for communication, they operate independently. I think in certain cases possible, but now if you want to use one system to achieve both, you need to coordinate different nodes. You need to manage resources carefully in order to avoid, interference between sensing and communication. That leads a lot of technical challenges as well, and some of them.
Yes, indeed. I was about actually, this was the part 2 of my question. Indeed, like, of course, having two systems, one system instead of two systems, as you said, rightfully, it's gonna, like, reduce the complexity of the system in the sense that we're gonna have one system, but at the same point, it's gonna increase, like, further challenges for the system, because we're gonna have one system to do both the sensing and communication. So yeah, that's
yes.
Indeed as you said. And then I go to my second question now. You were also talking about how the system should decide actually between local processing and edge offloading. Can you please expand further on how the system basically should decide on that?
Right. So maybe I'll just use this slide, although it's not exactly where I talk about offloading. Yeah, so that depends on multiple factors. One is whether you can afford to wait to, there may be some delay in transmitting the sensing sample to an edge server and then having the results sent back to you, and maybe your sensing sample need to wait in a queue at the edge server. So how timely would you require the sensing data processing result? And second is, it depends on what kind of load you can have. Like, if are you using an edge server to support many different sensing ISAC devices, is a resource limited compared to the sensing demand? And those things further depend on what kind of application we're talking about. If we're saying some kind of autonomous driving based ISAC, right, and we may not be able to wait for the sensing sample to be uploaded to the edge server and processed and sent back. So yeah, so it depends on the resource availability, the performance requirements, and among other factors.
Okay, thank you, Dr. Chi. My next question is about what is the main trade-off actually between sensing accuracy, resource usages, and the computational cost?
Right, that's a great question.
Yeah, the
So
$1 million question.
yeah, so first thing I'd like to mention is that trade-off. I mean, our case studies focused on some aspects of trade-offs, right? But they're not necessarily comprehensive. And one thing to also note here is when we talk about resource trade-off, we also need to consider whether the resource is shared. For example, we care more about the edge resource because edge resource may be shared between different ISAC devices, right? And we can have local ISAC computing resources, but those are not shared, so they're not part of the problem. So trade-off needs to be made with proper consideration of the resources, like especially for shared resources. We can use longer sensing durations or more spectrum for higher sensing accuracy, as long as our shared resources can support them. We have enough resources, we can coordinate the resources between different sensing nodes effectively. That again depends on the specific network scenario and the performance requirements.
Yes. Thank you, Dr. Chi. And as we usually do in our webinar series, actually, we ask our speaker for piece of advice for someone who is going to start a similar research. So in this case, what would you recommend focusing on first? It's going to be the data drift detection, resource management, edge learning, or the real world actually deployment challenges? What can you advise? How can you advise someone starting his work on EI empowered, actually, ISAC?
Right. Thank you very much. Maybe I can stop sharing my slides for that question. Yeah. So first, that's a great question. I want to first mention this. The work presented today, mostly from is most part of the PhD thesis of Professor Shisheng Hu now. He's also in the chat, so I'd like to thank him. So he is more, has more expertise than me in this area. I'll just mention what I'm interested in at the moment. So just two things. A large part of the ISAC research focuses on physical layer. And my exploration is more on the link layer. So I'd like to see how link layer designs would innovate, would improve ISAC performance. That's one thing I'm very interested in. Second is, so far our research is mostly AI for managing sense ISAC, right? I would be interested in the other way, the other direction. That is, how, suppose we're using certain AI applications, for example, autonomous driving. How do you design ISAC customized for that particular AI application? So that is also a direction I'm interested in. Yeah, so I guess those are the two things I can share here. Yeah,
I'm sure there are two important actually research directions, especially for someone who's gonna thinking about starting research in the same field. I think having some, the most difficult usually it's from where to start. So like starting from some point where maybe it's less explored area, if I may say, can be a good piece of advice actually for anyone starting or thinking to start research at the same field. So thank you one more time, Dr. Ji, for the insightful presentation on edge intelligence empowering integrated sensing and communication, 2 case studies with digital twins. Your work showed that digital twins offer a quite powerful, actually, pathway to make edge intelligence enabled ISAC more adaptive, proactive, and cost-efficient for sensing on the edge. Let me remind the audience that the recording of this webinar will be available soon, actually, on our VTS YouTube channel. Once again, thank you very much, Dr. Ji, for accepting our invitation and being our speaker today. We really enjoyed your presentation. Wish you all the best in your future endeavors, and thank you very much.
Thank you so much, Professor Chatelier, and I'd like to thank the audience again. Yeah, it's my great pleasure and honor to connect with a YP community.
Indeed, it was our great pleasure. Thank you, Dr. Ji, and
thank
wish
you
all the best in our future.
All the best to you.
Thank you. Bye-bye. Thank you very much.